There's a guy named Steve, and I'm about to make you get him completely wrong. Here's what I know about him. Steve is shy and withdrawn, helpful, but not super interested in people or the world around him. He's a meek, tidy soul who needs order and structure, and he has a real passion for detail. That's it. That's everything you get. Now here's the question. Is Steve more likely to be a librarian or a farmer? Sit with it for a second. Really, I'll even admit the first time somebody ran this on me, I answered without thinking, and I answered wrong. Confidently wrong. So if the obvious answer is already forming in your head, good. That means the trap is working exactly the way it's supposed to. Keep your eye on that gut answer, because in about a minute I'm going to show you why it's leading you off a cliff, and the reason has nothing to do with Steve at all. It has to do with a piece of information I didn't give you, and you didn't ask for, and honestly, most people never even notice is missing. Okay, be honest. You said librarian. Almost everybody says librarian, and I get why. Every word in that description sounds like it was written by a librarian's mom. Shy, tidy, quiet, loves detail. It's a perfect little costume. Steve fits the librarian shape so snugly that your brain just goes, yep, match done, next question. And that feeling of a clean match is so satisfying that you stop right there. Here's the thing your brain quietly skipped. It answered a different question than the one I asked. You asked yourself, does Steve sound like a librarian? And the answer is obviously yes. But that's not the question. The question was, is Steve more likely to be a librarian than a farmer? Those sound like the same question. They are wildly, catastrophically not the same question. And the gap between them is where basically all of human bad judgment lives. Doctors fall in it, juries fall in it. You are about to watch it swallow a perfectly reasonable answer whole, and the tool that pulls it back out is named after a guy from the 1700s who probably never met a farmer in his life. Here's the number nobody asked for. In the U.S., roughly, there are about 20 times as many farmers as there are librarians. I'm rounding hard, the exact figure doesn't matter. What matters is the size of the gap. For every librarian, picture 20 farmers standing behind them. So let's build a crowd. Say we've got 200 farmers and 10 librarians. That's our world. Now, yes, a random librarian is more likely to match Steve's shy, tidy description than a random farmer is. Let's be generous and say librarians match that description, 75% of the time? And farmers, sure, they're more outdoorsy on average, so let's say only 10% of farmers fit it. Watch what happens when we actually count, because this is the whole trick, and it flips the answer completely. Your gut compared the percentages. 75 is way bigger than 10. Librarian wins. Easy. But your gut forgot to multiply those percentages by how many people are actually in each group. And when you do that multiplication, the crowd does something your intuition never saw coming. Let's actually do it. 10 librarians, 75% of them fit Steve's description. That's between 7 and 8 people. Call it 7.5. Now the farmers, 200 of them, but only 10% fit that shy, tidy, detail-loving profile. 10% of 200 is 20 farmers. So freeze right here and just look. Among all the people who match Steve's description, 7.5 are librarians and 20 are farmers. 20. The farmers win, and it isn't even close. Nearly 3-1. So if you meet a shy, tidy, detail-obsessed person and you have to guess, farmer is the smarter bet. Not because Steve sounds like a farmer, he absolutely doesn't, but because there are just so many more farmers that even their scraps outnumber the librarians' best. The description was a spotlight pointing straight at librarians, and the correct answer was still farmer. That's the part that broke my brain the first time, being told something feels like a match and having the actual count laugh in its face. Now I want to give this a shape, because a pile of numbers is easy to forget and a picture is not. Draw one big rectangle. The whole rectangle is everybody, all 210 people. Now slice it left to right by job. A thin strip on the left for librarians, since there's only 10 of them, and a big fat strip for the 200 farmers. So far the widths just show how common each job is. That's the part your gut ignored. Now, inside each strip, shade the fraction that matches Steve. In the skinny librarian strip, shade most of it, 75%, a tall, bright block. In the wide farmer strip, shade just a thin sliver at the bottom, 10%. And here's the magic. The area of each shaded block is the actual number of people. Skinny but tall for librarians, wide but short for farmers. And when you look at the two shaded areas side by side, the farmer's sliver, low as it is clearly bigger because the strip it lives in is enormous. Bayes' whole theorem is just this. It's an argument about areas. So let's name the exact place your brain slipped, because it's a specific spot, and once you can see it, you'll catch yourself doing it forever. Your gut looked at the heights of those blocks. 75% tall versus 10% tall, and by height alone, Librarian crushes it. But height is the wrong thing to compare. Height tells you if you already knew someone was a librarian, how likely they'd fit Steve. That's a real number. It's just answering a question you weren't asked. What you actually want is area, because area folds in the width being how many of those people exist in the first place. Psychologists have a boring name for the width. They call it the base rate, and ignoring it is such a reliable human bug that it has its own name too, base rate neglect. It's not that people are dumb, it's that the description is loud and vivid and right in your face, and the base rate is a quiet little fact about population counts that nobody puts in the story. The vivid thing shouts, the number whispers, and we listen to whoever's loudest. Okay, now the formula, and only now, because if I'd opened with it, you'd have glazed over and I wouldn't blame you. Everything we just did in pictures, here it is in symbols. The chance Steve is a librarian given his description equals the base rate of librarians times the chance a librarian fits the description divided by the total number of people who fit the description from everywhere. Read it slowly. Top of the fraction, that's the tall, skinny block, 10 librarians times 75%, 7.5. Bottom of the fraction, that's every shaded block, added up 7.5 plus 20, so 27.5. 7.5 over 27.5, that's about 27%. So even with a description tailor-made for librarians, Steve is only 27% likely to be one. And I want to be honest with you, the notation for this theorem is genuinely ugly. Little P's and vertical bars everywhere. It looks like it's cursing at you. But every single symbol is just pointing at a block in that rectangle you already understand. The picture came first. The formula is only the receipt. Now, let me show you why this is more than a party trick about a fictional shy man. Swap the story. Instead of Steve, it's you at the doctor, and you just tested positive for a rare disease. The test is good. It's 99% accurate. The doctor looks grim. So, how scared should you be? Almost everyone, including a scary number of actual doctors, hears 99% accurate and assumes they're 99% likely to be sick. Same move as before, they compared the loud number and skipped the quiet one. So let's find the quiet one. The base rate. This disease is rare. Say 1 in 10,000 people actually have it. That's the width of your skinny strip, and this time it's razor thin. 10,000 people get tested. One of them, on average, really has the disease and the test correctly flags them. Great. But the test is wrong 1% of the time? 1% of the 9,999 healthy people is about 100 people. 100 healthy people who test positive anyway. So look at who's holding a positive result. Here's the picture I want you to screenshot, because this is the whole video in one frame. In front of you, one person who is truly sick, and 100 people who are perfectly healthy but got a false alarm. All 101 of them are holding a positive test. All of them got the grim look from the doctor. So if you're standing in that group, what are the odds you're the sick one? 1 out of 101, less than 1%. You tested positive on a 99% accurate test, and you are still almost certainly fine. Read that again because it feels illegal. It feels like the 99% has to mean something bigger. And it does mean something, it just means something about the test, not about you. The reason the sick person drowns in false alarms is the exact same reason Steve turned out to be a farmer. The rare thing is rare. When a group is tiny, even a tiny error rate applied to the huge, healthy crowd produces more false positives than there are true cases. The base rate wins again. There's a nicer way to think about what just happened, and it reframes the whole thing as a story about changing your mind. Before the test, what did you believe? You had no reason to think you were sick, so your belief matched the base rate. 1 in 10,000. That starting belief has a name. It's called your prior. Then evidence arrives, the positive test, and you update. Your new belief after seeing the evidence is called the posterior. And Bayes' theorem is just the exact recipe for getting from prior to posterior. Here's the beautiful part. The test really did move you. You went from 1 in 10,000 to 1 in 101. That's about a 100-fold jump in worry. That's not nothing. The test did its job. You just started from such a tiny place that even a big jump lands you somewhere still pretty safe. This is the honest version of updating on evidence. You don't throw out your prior and believe the newest loud thing completely. You don't ignore the evidence either. You multiply them together. New belief equals old belief, adjusted by how strong the evidence is. That's it. That's the engine. Now, one fair objection, because I had it too. If one positive test barely moves you, isn't the test kind of useless? No, and here's why. You take it again. Bayesian updating stacks. The posterior from your first test becomes the prior for your second test. You don't reset to 1 in 10,000. You start from 1 in 101 because you've already learned something. Run the numbers again with that new starting point, and a second positive shoves your odds of being sick from under 1% up to around 50-50. A third positive would push you past 90%. Each piece of evidence multiplies onto the last. This is why doctors retest before they scare you, and it's genuinely good practice, not just caution. It's also, weirdly, how a healthy mind is supposed to work. You shouldn't flip your whole worldview on one surprising fact, but you also shouldn't be immovable. You let each new piece of evidence nudge you, and if the evidence keeps pointing the same direction, the nudges add up until you've completely, correctly changed your mind. One data point is a whisper, a pile of them is a shout, and this time the shout is telling the truth. So here's where we land. Steve's a farmer, your positive test is probably fine, and the fix for both is the same tiny habit. Before you trust a vivid match, ask the boring question. How common was this thing to begin with? That one question, the base rate, quietly decides more arguments than any clever description ever will. But I want to leave you with the thing that still bugs me because it should bug you too. Every number I used, I made up. The 75% of librarians, the 1 in 10,000, all of it, invented for a clean example. In real life, where do those priors actually come from? Sometimes there's good data, but a lot of the time you're just guessing. And Bayes' theorem is perfectly happy to take your garbage guess and hand you back a confident, precise, mathematically flawless posterior that's completely wrong. The math is honest. It just can't protect you from a bad starting belief. So the theorem doesn't tell you what to think. It tells you how much to change, given what you already believed. And figuring out what you should have believed in the first place? Yeah, that one's still on you. See you next time.